Okay, so let us continue with state space search. So, let me just do a very quick recap and then we will continue from there. So, the state space is a space in which made up of many states, where each states represent a particular situation, and the states are connected together by the moves you can make or the decisions you can make. So that if you are in a given state and we had defined this function called move gen, which takes, so n we will use for a node in the state space. So, the state space is implicitly a graph. I say implicitly because it is not available to us, it is not that the graph has been given to us and we have to find a path in that graph. We are given a start state and we are given either a goal state or a description of a goal state. So, for example, in the river crossing problems we are given a goal state that everybody must be on the other side of the river, but on something like n queens we are given a description of the goal state which says that place n queens so that no queen attacks any other. So, either way we are given some idea about the goal state, and then the search algorithm explores this state space. And how does it search the state space? It applies the move gen function, which is a neighborhood function which gives you the neighbors of each state, and then you inspect one of the neighbors and see if that is a goal state that you are interested in. If not, then you generate more states and so on and so forth. So, this search state space search generates a search tree. So, the state space is a graph, at least implicitly it exists even though we do not have it with us, and the state space search generates a search tree, and we saw that this search tree is characterized by, so we start with some search node and then we go down searching for the trees. We had seen this before. So, obviously every tree has two kinds of nodes. So, one kind of node is we have called as open. Open is the set of leaves actually. The set of leaves we call as open, and the set of internal nodes we call as closed. The open list or set of leaves is the search frontier. That is the set of candidate nodes that you have generated, but you have not inspected. So, that we can think of the search frontier, and the set of internal nodes is the memory of past nodes visited. So, I will just call it seen nodes. So, we started off by saying that open and closed are sets. Then because we want to implement this using some algorithms, we said let us call them lists essentially. And as we will see today, a list notation is not necessarily, I mean a list structure is not necessarily the best structure. We will come to that in a little bit of a while. But basically the search space is, the search tree is characterized by these two, let us call it sets or lists or whatever, open and closed essentially. And just to recap the algorithm, we extract, so we had moved from storing only the states to a pair of states, and the pair consists of a given state and the parent state. So, the parent state is a state from that given state was generated essentially. So, we have this node pairs. We said that initially open gets this pair of start comma nil. So, I will just write the outline today, and then while open not empty. If it is empty, then you return failure. When will it be empty? It will be empty only for finite state spaces, that you would have ended up by inspecting all the states and none of them happens to be the goal state, in which case it will be empty, and then you can say that the goal state cannot be found. So, for example, in the 8 puzzle I had pointed out that the state space is actually partitioned into 2 sets of states which are connected to each other. So, one set is not reachable from the other set. So, if you gave the start state in one set and the goal state in the other set, then it would not be reachable, and you would end up inspecting all the nodes reachable from the start state and say that we know we cannot solve that problem. So, if open is empty, then you return failure. That will happen at the end, we will not write it here. Otherwise, we get node pair as head of open. I will not write the details. We did a little bit in the last class, and otherwise you can look up the book. From this node pair, we extract a node, let us call it n, which is the first element of the node pair, and we apply the goal test n. We apply the goal test function. So, remember that the goal test function takes a node and tells you whether it is a goal node or not. So, somehow you have to implement the goal test. So, move gen n and goal test n, these are the 2 domain functions that we have. The rest of the search algorithm that we are writing is independent of the domain. As long as somebody provides you with this move gen function and the goal test function, you can use this algorithm to solve problems in any domain essentially. So, you do the goal test. If it is yes, then you reconstruct the path. If it is no, you apply move gen to n and you get some successors, you get the neighborhood of this node n, and to this you do some filtering, you remove the things that you have seen. So, I will just say remove seen. So, there is some function which will take the output of this and filter out things which are already existing in closed or in open essentially. We do not want to generate the same node again, because if it is closed, if it is in closed, we have already seen it, and if we inspect it again, we are likely to go into a loop. If it is open, we will see it some time, because it is on open anyway, no point keeping 2 copies of it in the open. So, this remove scene basically removes both from open and closed the successors of n, and then we have a function called make pairs. Whatever remains after this filtering, we make pairs. What is the pair? So, this node, we take this node n as the parent of each of these nodes inside this. So, these nodes will look like x comma n, because n, these are all the children of n. So, n should be the parent of these nodes, and then we add this thing to open. Or to the tail of open, if you want to be precise, because if you remove the head, we have not removed the head here. So, actually you should add it to tail of open, but anyway that is the basic idea. And then we saw that there are 2 ways of doing this. One is as a stack and the other is as a queue, which means that you either add the new ends at the head of open, then it behaves like a stack, because they will be the first ones to be inspected, because we are always extracting the node from the head of open. And when it is a stack, we saw that this behaves like depth first, and when it is a queue, we saw it behaves like breadth first. So, what was the characteristics of depth first and breadth first? Depth first basically dives into the search tree, and breadth first is more cautious, it sort of plods through this thing. So, these were the 2 characteristics of these 2. So, you can say depth first is impetuous, it just goes where it is nose takes it, so to speak, and breadth first stays close to the start state essentially. Then we had looked at the properties of these two algorithms. So, we want to compare properties on two features. One is time complexity. Now, time is bad for both. By bad we mean the worst case situation or the average case situation. In the best case they will find the goal. So, for example, depth first search might find the goal state in this branch itself, in which case it would find it in linear time, or breadth first must find the goal state somewhere here which is very close to the start state, and it will find it very quickly essentially, but that is the best case. On the average case and the worst case, this time complexity for both is of the order of b raised to d, where b is a branching factor and d is the depth at which the goal occurs essentially. We saw there was a little bit of a difference. The breadth first search had slightly more time complexity than depth first search, but it was only slightly more essentially. So, this is something that we will start addressing today a bit later. We saw time complexity, we saw completeness, and by completeness we mean will it find the goal state or will it find a path to the goal state if one exists, and the answer in the case of breadth first was unequivocally yes. In the case of depth first it is guaranteed to find the goal state for finite state spaces, not for infinite state spaces, because in infinite state spaces they could go off in some infinite loop or some infinite branch. So, we will assume that we are working with finite state spaces and we will answer yes to this, but keep in mind that this is only for finite state spaces essentially. Then we saw two more properties, one is space complexity, and we found that space was good for depth first because it keeps only, it adds only a constant number of nodes as it goes down, because if the branching factor is b, it goes down, it will add b nodes, inspect one of them, then again add b nodes, inspect one of them, and so on and so forth. It adds b nodes, which means the space required grows linearly, whereas breadth first search will first inspect the entire row, generate children of all those nodes. So, it will become b into whatever the width of that was, and therefore, it multiplies by b as it goes down deeper and deeper, and therefore, this goes exponentially. So, this was a plus point for depth first search, but quality was a plus point for, so I will just write plus here for breadth first search, because of the fact that breadth first search only plods slowly into the search space. At whichever layer the goal node occurs, it will find that path to the goal node essentially, which means it will always find the shortest path to the goal node. And I hope you have convinced yourself by constructing a toy example. If you have not, please go and do it essentially. So, this is what we did last time. So, there are two things we want to do today. One is try to see if you can find an algorithm which will combine these two plus points, and the other is to try and address this time complexity somehow, because if you have an exponential time algorithm, nobody is going to buy it essentially. You can only solve very small problems with it, not problems of any significant size. So, let us first look at this. Is there an algorithm, did anybody give a thought to this, which will combine these two properties of depth first and breadth first, which means require linear space, but guarantee an optimal solution? Okay. So, I take it you have not been reading my book yet. So, let us look at some variations of this. All the algorithms that we are looking at today are blind search algorithms, which means that they have no sense of direction. They always, so if given a state space, if this is a start state and this is a, and wherever the goal state may be in this state space, the behavior of the algorithm would be the same. So, depth first would go off in that direction, backtrack, try something else, backtrack, try something else, and so on. Breadth first will go round and round and round till it expands. The goal could be here, the goal could be here, or the goal could be this side, it does not matter. So, that is essentially. So, let me introduce one new algorithm or two new algorithms. One is we will call depth bounded. So, it is just a variation on depth first search, and the variation is that we have put a depth bound. Do not go more than 20 steps, go and go more than 40 steps or whatever, some depth bound we have put and said. So, what have we done? We have cut off the search tree at some level, and we have said that do depth first search on this truncated search space. What is the characteristics of this algorithm, depth bounded depth first search? It is linear in space. Why? Because it is depth first search to start with. It is complete. Yes or no? So, one no and a few yeses. So, who said yes? Why is it yes? What is the meaning of complete? We said that if there is a path, see, this depth bound is something that you have imposed, it does not come from the problem. The goal could have been somewhere here, you know. What is the depth bound? Depth bound says that it is like a Lakshman Rekha, do not go beyond this line. So, if you find the goal within that, yes, you will get the solution, but if the goal happens to be outside that, like here, which could be somewhere here, then you will not find the solution. So, obviously, it is not complete, but it is space efficient because it is depth first search. Now, let us do a variation. Okay. Let us have an algorithm in which we say depth bound is equal to 0. So, this is a new algorithm I am writing. We initialize depth bound to 0 and then we say while goal not found, do this algorithm. So, let us call this DFS, and let us say this is the depth bound DB. So, let me use DB here also. So, this is the algorithm. It takes an argument, of course, it takes a start node and everything, but that we will assume is hidden or global or whatever. So, while the goal not found, do depth bound depth first search with the bound DB. So, 0 means you just inspect the start node, 1 means you go one level deeper, 2 means you will go 2 steps deeper and that kind of stuff. And then you say so, we have this put this in a loop, right. So, this is a new algorithm. What is this algorithm called? It is a very well known algorithm. It is called, so I will write it here in case we need that space, iterative as the algorithm suggests. So, this is called iterative deepening. In every cycle you increase the depth bound by 1 and then do a depth first search. So, iteratively you deepen this bound to which you will search essentially, and because we are doing depth first search, this is called depth first iterative deepening, which is popularly known as DFID. So, this is algorithm DFID that we are writing. So, first you should understand what the algorithm is. We are doing a sequence of this depth bounded DFSs, starting with depth 0, then going to depth 1, then to depth 2, then to depth 3, and so on and so forth. So, what is the properties of this algorithm? So, let us talk about, we will come to time complexity in a moment. Let us talk about space, and let us talk about quality. These are the two quantities we were interested in here, because breadth first gave us an optimal solution, guaranteed an optimal solution, good on quality. Depth first was space efficient, required only linear space. What about DFID? Space complexity. When we say space complexity, we mean the size of open. So, that is the convention we have been following essentially. Come on. Same as DFS. Why? For the simple reason that it is DFS. Of course, it is not one DFS, it is many DFSs. Every time you do a different DFS with a different depth bound, but you are doing DFS. So, space is linear. So, does anyone have a doubt about this? So, you should clarify this at this moment itself. It is just doing a series of depth first search. Inside every cycle in this loop, it is doing one depth first search, but it is doing depth first search. So, it must be requiring space complexity of depth first search, which is linear essentially. Okay, what about quality? Quality, not completeness. Does it guarantee an optimal solution? Does it guarantee a shortest path? There is no depending upon. I have given the algorithm completely. I am asking you the question that this algorithm, does it guarantee you an optimal solution? Yes. Oh, that is a very resounding yes. Anybody in Mandi? So, okay, what is the argument behind this yes argument? Yes answer? Okay, anyone willing to talk about why does it, how does it guarantee? Yeah, so the answer is, what is the behavior of this algorithm? If you look at only the new nodes, now what is this algorithm doing? It is going to re-inspect many nodes. So, let us say we have a search tree in which we start with S, then in the first round we look at only S, then in the second round we look at S, A, B, C, then in the third round we look at, let us say this is D, E, F and so on and so forth. In this third round, what is the order in which you, so in the first round it would inspect only S in the first cycle. In the second cycle it would inspect in this order S, A, B, C, sorry S, then S, A, B, C. In the third round it will inspect them in S, then S, sorry that was correct. S, then A, then D, then E, then F, then B, and then whatever the child of B is essentially. So, in the first cycle it inspects only S, in the second cycle it does search only till this depth. So, S, then A, then B, then C. In the third cycle it inspects at this depth. So, I have not drawn the complete tree, but S, A, then D, then E, then F, then the children of B, then the children of C, in that particular order, that first order. But this thing. Now, if you were to mark the order in which it first time visits a node, then you can see that S is visited in the first cycle, then A, B and C are visited in the second cycle, then D, E and F are visited in the third cycle, and so on and so forth. So, the order in which it is visiting new nodes, if you look at the order inside this red circle, if you can see that S, A, B, C, D, E, F, S, A, B, C, D, E, F, this is the order of breadth first search, and if it finds the goal, it would have found the shortest path essentially to the goal, because we know that breadth first search in this order, always level order as we also call it, always finds the shortest path. So, you must convince yourself, I think, that this algorithm DFID combines both the things that we desired, which is that space should be linear, which was in depth first search, and quality, that it should guarantee the optimal solution, which breadth first search is, and this is actually giving it to us. So, you might say that this is actually a sequence of depth first searches masquerading as a breadth first search essentially, because the behavior in terms of the paths that it finds would be the same as what breadth first search would have done essentially. And because the very first level at which the goal appears, this will terminate, we know that it has found the shortest path essentially in the goal. So, any questions here? Okay. Yeah. So, what I have written here is while goal not found, and so I have glossed over some detail. If let us assume it is a finite graph, it is an infinite graph, it will keep searching, right. So, let us assume it is a finite graph, then I will leave this as a small exercise for you to discover that at which point no new nodes are being added, which means if you just inspect the next layer, if there is no new node, then you have inspected the complete graph. If you have inspected the complete graph, it should report failure, but till that point it should keep deepening and searching till it finds a goal.
So, overall it will repeat as the number of, as the height of the tree.
It is not a tree, it is not a tree, it is, we do not know where the goal is, that is the whole idea for the searching. We are in some space and we are exploring the space by using the moveGen function, and we were trying to find a path to the goal. So, first of all, we do not even know whether a goal exists. For example, in that 8 puzzle I might give you the goal state as one which is not reachable, and secondly we do not know where it exists, at what level it exists. So, the whole idea is to search for the path essentially, I think. You know, this iterative deepening algorithms, they were devised in a chess playing situation essentially, and so you know we saw when we are looking at the history of AI that chess playing has long been a fascination with AI people, and they want to make the programs play tournaments under tournament conditions, and tournament conditions, for those of you who play chess, know that you are allotted a certain amount of time for making a certain number of moves essentially. So, the time available to the player is fixed essentially. Now, we will see game playing programs later in this course, but essentially they also explore a tree of some kind, and they can also explore a tree up to various levels of depth. The deeper they explore it, so exploring a tree basically means you explore combinations of, if I make this move, then the opponent will make this move, then I will make this move, then the opponent will make this move, and so on. So, obviously this kind of analysis you can do to any level till the end of the game in fact, but that is not really possible. So, you do this analysis, and then try to judge which is the good move to make essentially. Now in chess playing programs, if you are playing under tournament conditions, you have to be aware of how much time you have essentially. So the iterative deepening algorithms were devised to cater to that situation, that you run the algorithm and let it go deeper and deeper as long as time allows. Suddenly if the calling program knows that the time is running out, it will say tell me the best move, and it will play the best move essentially. So we will look at iterative deepening again, or at least we will mention it again when we look at the game playing algorithms actually. Now
Why do you need to always begin from S in every iteration? You already visited S in the first iteration. Next time you remove it.
so you are saying why don't you do breadth first search? But the reason why we are not doing breadth first search is because it needs to store this entire. See, what is the open list of breadth first search? The open list is something like this across this tree, and this is a shape. So the search frontier for breadth first search in fact looks like this, and as we go deeper and deeper, this is growing exponentially. We know that the number of nodes in the here are b raised to d essentially. So we do not want to store b raised to d nodes. That is the reason why we are not doing breadth first search. So we are doing depth first search, but so
From S again, you already visited S.
you already visited S, but what is the option available to you? So if you think a little bit about it, you will see that, see I can see what you are trying to say. You are trying to say that what is the point of starting with S all over again, but where do you start otherwise? In breadth first search, you would have inspected all these nodes, and then you would have inspected their children. Where would the children be? They would be in open, but here we do not have them essentially, I think. So you need to give a little bit of thought to it. Yes, that is a common doubt when we look at DFID first essentially. So we are doing this extra work. What is this extra work we are doing? That we are doing a sequence of searches in which we are inspecting the complete tree at every level. So first up to level here, then this whole tree, then this whole subtree, then this whole tree, and so on and so forth. So obviously we are paying an extra cost. Is this cost worthwhile? What is the benefit we are getting? The benefit we are getting is that we are getting linear space and optimal guarantee of optimal solution. But the extra cost is going to be the price that we pay of inspecting all these nodes which are not inside these red circles again and again. So S we have seen here, again we are seeing it here, again we are seeing it here. A we have seen here, we are again seeing it here. B we are seeing here. This whole count is the count of measure of time complexity of DFID, because we are seeing all these, inspecting all these nodes. So how much is this extra cost? Is it worthwhile is the question. What is your intuition? So let me repeat, in DFID we search up to some level, let us say this level, we do DFID at some, for some depth bound we come up to here, and then to inspect these next level nodes we search this whole tree again, including this for the. So this shaded portion is the extra work we are doing for inspecting this new set of nodes. How much is this extra work? Is it high or low? Okay, let me just ask a very simple question. So we have to go back to our study of trees, and you might have done in data structures or some other course. Let me take an arbitrary tree of branching factor B. And we will take a complete. So for this argument sake, we will assume that the tree is complete, which means every internal node has exactly B children for the sake of analysis, which is not the case, as you know. For example, in the 8 puzzle corner, when the blank is in the corner, there are only 2 moves that you can do, whereas when the blank is in the center, you can do 4 moves. So obviously the branching factor is not constant, but let us assume for the sake of analysis that the branching factor is B and it is constant. So and this is a frontier that we are looking at. So which is the set of leaves, as we have said, right? The leaves of this tree are is the search frontier, and the internal nodes I of this tree are the nodes that we are visiting again for the sake of inspecting these L nodes essentially. So, at any given stage, what this is what breadth first would have done. Breadth first search would have just inspected these L nodes. What is DFID is doing? It is inspecting I plus L nodes essentially. That is the extra work it is doing. The whole question is, and that is should give us insight into the nature of this monster that we can call combinatorial explosion. So, let me give you a nice argument. Of course, I am sure you have done this in some course. What is the ratio of internal nodes to leaves in a complete tree? But I remember a mathematics professor K. Joshi from IIT Bombay had given a very nice argument, and you can visualize a tournament which is going on. So, since the branching factor is B, we will assume that it is something like let us say 100 meters sprint or something like that, and at any node there are B children. So, any such thing can be seen as one game or one race that you want to call. If it was binary, I could have talked about a tennis tournament, but it is not binary, it is branching factor is B. So, let us assume it is like a 100 meter sprint and B people compete in a heat and only one is selected from the top essentially. So, that is the nature, the ruthless nature of this competition. So, there are totally L competitors, and in every internal node I, what happens? Every internal node is a heat. In every internal node, one out of B goes ahead and the B minus 1 are eliminated essentially. And in the end, of course, there is only one winner in the end, and all the rest are, should I use the word losers, or we should say also ran, maybe I think that is a better word, this thing. So, if you give some thought to that, you will see that the total number of participants, which is L, which is the number of leaves in our tournament. So, these are also called winner trees, you might have studied them somewhere actually, is equal to V minus 1 into I plus 1. So, what is the argument for this? Of course, you can give a proof by induction if you are more mathematically inclined, but this argument is just a tournament argument. It says that in every internal node B minus 1 players are eliminated. So, if I is the number of internal nodes, then B minus 1 into I is the total number of players which are eliminated, which is of course L minus 1, and there is one winner. So, who stands out? So, the total number of competitors is given by this, and this gives us a relation between I and L. So, you can write I is equal to L minus 1 divided by B minus 1, and then you can compute L plus I divided by L, which is a ratio that we are looking at, which is the amount of extra work DFID is doing as compared to breadth first search. Breadth first search would have inspected only L nodes, only this boundary nodes. DFID is inspecting the entire tree, which is L plus I nodes essentially. So, if you write this, plug it in and do a little bit of simplification, you will see that this is for large L B over B minus 1 approximately. There is a small factor somewhere which I will leave out essentially. So, what are we saying? We are saying that the amount of work which DFID is doing as compared to breadth first search is negligibly more essentially, just B over B minus 1 times more essentially, and that should not be surprising to you, because this is the nature of this beast, this combinatorial explosion, that we have B raised to D nodes here in this layer, and all the internal nodes are B raised to D minus 1 by B minus 1. So, if you ignore that minus 1, let us say for large depth or large branching factor, you can ignore that. You can see that L is roughly b minus 1 times I, which is also what we have written here. So, the number of leaves as you go deeper down a tree is b minus 1 times the entire set of nodes that you have seen before essentially. Everything you did before pales in comparison to what you are doing at this level essentially. So, what and that everything you did before is the extra work which DFID is doing, it is just visiting those nodes again and again essentially. And if you go through this argument, you will see that the time complexity of DFID is not significantly more than breadth first search. We had seen that breadth first search was a little bit more than, so BFS to DFS we had said was b plus 1 over b or something like that. I do not remember exactly, but I think b plus 1 over b. Breadth first search is doing little bit more work than depth first search, and DFID is doing only a little bit more work than DFID. And what is the advantage we get? We are allowed to use linear space and we are guaranteed the solution essentially. Okay, so it is a very nice algorithm. You can think about this a little bit. I want to before we move on to this other question of how can we get around the time complexity, I want to address this question. This thing that we did, remove scene. What is remove saying is that for every new child that you are generated or every new node that you are generating, check whether it is already present in closed. Okay, so let us assume that we have a simple collection of nodes and we do not have these node pairs and so on. Let us just ignore that for the moment, but we have a collection of, we want to check whether the given node is existing in closed. What is the cost of this action or complexity? Are we paying a heavy cost for simply checking whether we have visited a node again? How, what would be an algorithm for doing this? So, what is the task? The task is given a new node n and given a list of nodes which we call closed, which is the nodes that we have seen before. Well, I use the term list, but we could have used set, and it does not matter whether n exists in that set or list or not. What would be the algorithm for doing that?
We can create an array and in which we can store this node has been bit vector in which we can store if this is being visited. So it would be order 1 access time.
Okay, we will refine that in a moment. But if I treated it as a list, how would I do it? I would have to sequentially search, which would mean it would be linear in the size of closed. And how is closed growing as depth? Closed, remember, is a measure rough. So that is why when we said that when we talk about time complexity, we will approximate it with the size of closed, which means the number of nodes that we have. What is closed? Closed is the nodes that you have already seen, and we had said we will approximate it with the size of closed, and there we had made an assumption that checking in closed is not expensive. But if closed is going to be expensive, checking in closed is going to be itself, if closed is growing exponentially, then checking in that will each time will take exponential amount of work, then it is going to be a tough thing to crack essentially. So there is I want to make a distinction between when conceptually we think of closed as a list, it is fine as far as the problem solving algorithm that we are considering essentially, but if you were to put on your software engineer or programmer hat, then you have to be more concerned about how to implement closed. So obviously set is not a good idea. Anyway, sets you have to implement in some way or the other. List is not a good idea because we will have to scan through the list, and we will take a queue from what she said. Can we do this faster? I am not saying that we should make an array of bit vectors. You should be a bit louder and a bit more confident when you make such answers.
We have a binary search tree or something.
Yeah, well, a binary search tree would assume that the given set is an ordered set, because you need to have this thing. But a hash table is the perfect solution to this. You must implement closed as a hash table, even though we say it's a list and that kind of stuff. That's only for discussion purposes. But if you are going to implement the algorithm, then closed must be a hash table, and we know that on the average, if you design your hash table well, if your hash function is nicely chosen, then it will give you average constant time retrieval from there essentially. We will come to open again in a little while. So, I keep talking about this as a monster and a beast. So, what is the size of this problem? So, let me give you some idea about this. If you look at the Rubik's cube, remember that b is equal to 18, and Rubik's cube is a nice example where b is constant. At any given state you can make these 18 possible different moves, 3 for each face, and there are 6 faces. If you have to search up to a depth of 10, which means you want to explore the space up to depth 10, then you would have 18 raised to 10, and that turns out to be 3.5 into 10 raised to 12. If you are searching for in the Rubik's cube, that what will happen if I try all combinations of 10 moves that I can do, then you have to inspect about 10 raised to 12 states essentially. And what is the typical length of a solution? Any idea of a Rubik's cube problem? Is it less than 10 or more than 10? It is more than 10 most of the time. If you were to search for depth 20, this, and let me get, I have the number somewhere, is 1.27 to 10 raised to 25. How long does it take you to inspect 10 raised to 25 nodes? You know, we do not have a good idea of big numbers. 10 raised to 25, 10 raised to 30, they all sound same to us. So, let us say we assume, do some very rough calculation. Let us say we can inspect 1,000,000 states in a second. So, we will need 10 raised to 19 seconds. Let us assume we do not want to divide by divide by 60 and all. Let us assume there are 100 seconds in a minute. So, we will have 10 raised to 17 minutes, and let us say there are 100 minutes in an hour, then we have 10 raised to 15 hours. Let us assume that there are 100 hours in a day, then we have 10 raised to 12 days. How many days is 10 raised to 12 days? Let us assume that there are 1000 days in a year, it is 10 raised to 9 years. It is about a billion years. If you had to, if you had a machine which could inspect 1,000,000 moves per second and it had to explore up to a depth of 20, according to this calculation it would take you about a billion years. But if you do the actual calculation, and I did it at home, it actually takes 40 billion centuries to inspect 18 raised to 20 nodes essentially. To inspect 10 raised to 25 nodes, it will take about 40 billion. I am sure you are not willing to wait for so long essentially. So, we will try and address this. How, and I said people have more recently written programs which will find you the optimal solution in a Rubik's cube essentially. How do they do it essentially? So, that is answering this question. How do you attack this exponential time complexity? Can you sort of improve upon that essentially? So, we will do that in the next class, and we will take a break now, and when we look at heuristic search essentially. So, we will take a break and come back in about 5 minutes.